Tesla just shattered every rule of car manufacturing. The Model 2's assembly line doesn't look like a factory. It looks like a giant Lego set. 4 massive modules snap together in minutes, where traditional cars need 20 hours and 1,500 parts. Front casting, battery pack, drive unit, interior cabin, each built separately, then combined like plug-and-play blocks. How does this slash production time by 50% while cutting defects by 40%? And why are competitors calling this approach impossible to replicate? Let's dive right in. For over a century, car factories followed one sacred rule: build the vehicle piece by piece, station by station, in a single long line. Ford invented it. Toyota perfected it. Every automaker on Earth copied it. Until now. What Tesla's doing at Giga Texas breaks this rule so completely that when automotive engineers first saw the leaked layouts, many called it theoretical or staged for PR. But the production line is real, it's running, and it's about to make the $25,000 Model 2 the most profitable small car ever built. The secret? Treating a 3,000-pound vehicle like a 4-piece puzzle instead of a 1,500-part nightmare. Traditional car assembly is chaos managed through precision. A typical vehicle body arrives at the paint shop as a shell made from over 400 stamped metal pieces, welded together by 200-plus robots across dozens of stations. If one robot miscalibrates, the entire line stops. If one part arrives late, 50 workers stand idle. This is why most automakers need 20 to 30 hours just for mechanical assembly. What if there was a completely different approach? Tesla's compact modular line doesn't work sequentially. The Model 2 exists as 4 independent mega-modules built simultaneously in separate cells, then combined in one final assembly zone. While traditional lines build the body first, then add the battery, then install the interior, CML builds everything at once in parallel streams. The time savings are staggering, but the quality improvements might be even more important. The frame module showcases this revolution clearly. Instead of welding together 100-plus stamped parts with over 1,000 spot welds, Tesla uses 2 massive aluminum castings produced by 9,000-ton Giga press machines. What used to require an entire welding department now comes out as a single piece every 2 to 3 minutes. The structural battery pack, using Tesla's new aluminum-ion cells, bolts directly between these castings. 3 major components replace what used to be 300 individual parts. How much does this reduce potential failure points? The Powertrain module demonstrates equally dramatic simplification. Motor, inverter, gearbox, and cooling system arrive pre-assembled and tested as one complete unit. Instead of installing these components individually inside the vehicle over 45 minutes, the entire drive module drops into place with 4 bolts and 2 electrical connectors in under 5 minutes. This isn't just faster, it's fundamentally more reliable because the module was tested before installation. The interior module might be the most radical departure from conventional thinking. Dashboard, seats, climate controls, wiring harness, center screen, and door panels arrive fully assembled on a separate jig, already tested for electrical continuity. The entire cabin lowers into the vehicle as one piece, eliminating the cramped, time-consuming process of reaching inside the car to install dozens of individual components. Traditional automakers still have workers crawling inside partially built vehicles for hours. Tesla eliminated that entire step. This architectural shift transforms the factory layout completely. Instead of one continuous line stretching 500 meters, you get 5 compact cells, each roughly 50 meters across. Frame cell, battery cell, drive cell, interior cell, and final assembly cell. Each operates independently with dedicated teams, specialized robots, and specific quality checkpoints. When one cell encounters problems, the others keep running. Can you see why this matters for production stability? The numbers reveal CML's true impact. Total part count drops from roughly 1,500 distinct components down to 50 to 70 major assemblies. Every eliminated part removes one potential source of misalignment, cracking, or incorrect installation. Assembly defects fall by 30 to 40% compared to Model 3 production. These aren't projections. They're measurements from early CML test runs at Giga Texas. Speed follows naturally from this simplification. Traditional lines need 20 to 30 minutes just for interior installation because workers must reach into tight spaces and route wiring through confined channels. CML's pre-built interior module cuts this to 3 to 5 minutes of crane positioning plus connector clicks. Total assembly time per vehicle drops from the industry standard of 20+ hours down to just 10 hours. Same factory footprint, double the output, better quality. What does this mean for production costs? The maintenance advantage catches most analysts by surprise. On sequential lines, every station depends on the previous one. A single robot failure shuts down 40 stations downstream, idling 100+ workers while technicians troubleshoot. Maintenance and downtime typically consume 10 to 15% of total production costs. CML's modular cells isolate failures completely. If the battery cell goes down, the frame cell keeps running, the interior cell keeps running, and final assembly draws from buffer inventory. Uptime jumps from 85% to 95%, cutting per-vehicle production costs by 5 to 7% on maintenance savings alone. Tesla built something even more valuable than speed into CML: early error detection that legacy automakers simply cannot replicate with their current infrastructure. Traditional lines test the complete vehicle at the end. If the battery management system throws an error code, technicians must remove interior panels, disconnect the pack, diagnose the problem, then reassemble everything. A 4 to 6 hour process per vehicle. CML tests every module before integration. The battery module undergoes voltage checks, insulation resistance tests, and thermal imaging while still in its build cell. The drive unit runs on a dynamometer, verifying torque output and cooling performance. The interior module completes full electrical diagnostics with every screen, switch, and sensor checked before it ever approaches the vehicle frame. Defective modules get flagged and replaced immediately while the frame continues through assembly with a different module from the buffer. This approach cuts post-assembly rework by over 50% and catches quality problems at the source, where they're cheapest and fastest to fix. The final assembly zone operates with precision that would impress aerospace engineers. Instead of workers walking alongside a slowly moving vehicle, the frame sits stationary on a servo-guided platform. Robotic arms position modules with sub-millimeter accuracy using alignment pins and datum surfaces. High-voltage connectors click into place with automatic verification. If the connection isn't perfect, assembly cannot continue. This eliminates human error from the most critical connections. Once modules install, vehicles enter an integrated test lane running comprehensive diagnostics, high-voltage insulation, battery management operation, motor response, safety sensor calibration. Infrared cameras scan for thermal anomalies that indicate poor contacts or faulty components. Light load dynamometer tests verify powertrain performance. High-pressure water spray confirms zero leaks in the cabin, battery compartment, and drive areas. Problems caught here never reach customers. Here's what makes CML truly devastating for Tesla's competitors. It's designed for perfect replication. Every module cell uses standardized equipment, identical robot programming, and uniform quality protocols. Once Tesla perfects CML at Giga Texas, they can copy-paste the entire system to Berlin, Shanghai, or Mexico with minimal adjustment. A Model 2 from Texas will be mechanically identical to one from Berlin because both factories run the same specifications. Traditional factories can't match this consistency because each facility develops its own quirks and workarounds over time. Giga Texas serves as the proving ground where engineers refine module partitioning, optimize cell layouts, and establish quality standards. Once the system stabilizes at target output, 600 to 800 vehicles daily, roughly 200,000 units annually at full capacity, Tesla will deploy CML globally. North America gets priority for market demand and tariff avoidance. 2 or 3 CML lines across the continent could produce 500,000 plus Model 2s annually, while minimizing logistics costs. Berlin follows with European-specific refinements. The real advantage hiding beneath all this hardware is the AI orchestration layer. Each component carries IoT sensors, feeding real-time data to load balancing algorithms. Actual weight, station dwell time, equipment status, fault frequency. When the battery cell starts forming a bottleneck, the system automatically reduces frame flow to that cell, redistributes modules to cells with spare capacity, and triggers maintenance alerts. The line self-optimizes without human intervention, maintaining steady throughput and quality. Legacy automakers face an impossible challenge copying this system. Their factories are built around sequential processes. Their suppliers deliver hundreds of small parts, not large modules. Their workforce trains for traditional assembly. Converting existing infrastructure to CML would cost billions and require months of production shutdown. Tesla designed the Model 2 around CML from day one, optimizing every component and connection point for modular assembly. You can't retrofit this approach onto existing vehicles without complete redesigns. Will the Model 2's production system force every automaker to abandon traditional assembly lines? Or will Tesla's approach remain too complex for competitors to copy? Drop your prediction below. So here's what this actually means. Tesla didn't just invent a faster way to build cars. They've created a manufacturing system that legacy automakers physically cannot copy without burning their entire business model to the ground. While competitors are still debating whether to invest in EVs or hedge with hybrids, Tesla's building factories that produce twice as many vehicles in half the time with better quality. The Model 2 isn't just an affordable EV. It's proof that the Lego approach works at automotive scale. And this is just the beginning. Once CML stabilizes at Giga Texas over the next 12 to 18 months, expect rapid deployment across North America and Europe. By 2027, Tesla could be producing over 1 million Model 2s annually, while traditional automakers are still tooling up their first dedicated EV platforms. The cost advantage, the quality gap, the production speed, it all compounds into a competitive moat that gets wider every quarter. But here's the question that keeps industry analysts up at night. If Tesla can modularize a complete vehicle down to 4 main assemblies, what stops them from applying this same logic to the Cybertruck, the Roadster, or even future robotaxi platforms? CML isn't just a Model 2 strategy. It's a template for everything Tesla builds. Next, what do you think happens when other automakers realize they need to spend $10 billion redesigning their factories just to match Tesla's 2025 production efficiency? Will we see a wave of partnerships, or will legacy brands try to build their own modular systems from scratch? This is Tech Revolution, and we break down the engineering breakthroughs reshaping transportation and manufacturing. If analysis like this helps you see where the industry's actually heading, you know what to do. The next few years will separate the companies that adapted from those that didn't, and you'll want to catch every development as it happens. The assembly line just got completely reinvented. Everything downstream from here changes faster than most people expect.